Math 2414, Parametric Curves, Video 3, Eliminating the Parameter. At the end of the previous video, in the previous video, we took these parametric curves. Hold on, let's highlight them. We took these parametric curves. We created a table of values, which has since been erased, where we selected values for t, calculated x and y, and sketched the curve that you currently see on the screen. The curve had an orientation of starting from the bottom right corner of it, excuse me. Let's see how this looks. And traveling in this direction. We know it was traveling in that direction because the orientation describes how the curve is traced out as the values of t increase. There's t equals -2, -1, 0, 1, 2, 3, and 4. You notice I had to speed up to get from 3 to 4 because they're further apart, but we'll talk about that when we discuss calculus with parametric equations. But the thing we kind of left off was this looks like a parabola. And we really have no reason to doubt that it's a parabola. I mean, the parametric equations, one of them is quadratic, one of them is not. But in order to verify that it actually is a parabola, I would like the equation of the parabola in rectangular form, meaning in x's and y's, not parametrically. So how can we do that? How can we verify there is one equation that gives us this parabola? We can do what's called eliminating the parameter. Eliminating the parameter is basically taking your parametric equations and doing some algebraic manipulations to make the parameter disappear. Translation, get rid of the t. Now there's more than one way to eliminate a parameter, and as we go through this series of videos, I will continue this list of ways to eliminate a parameter. Ways to eliminate a parameter. I can't type this afternoon. All right, way number one, which is the only way that we're going to discuss right now, is to solve one equation for t and substitute into the other equation. Almost like you're solving a system of equations by substitution, which is kind of what we're doing right now. So if we were going to do that, then we would need to pick an equation that we want to solve for t. Now, of these two parametric equations, which one's going to be easier to solve for t? The answer should be clearly the second one. If we solve this for t, we'll get t equals y minus 1. And now that we know what t equals, we can substitute that into the other equation. The other equation starts out x equals t squared. But instead of t, we're going to write y minus 1 squared. And then minus 2, instead of writing t, we're going to write y minus 1. At this point, we technically have a excuse me, a quadratic equation, but I would like to go ahead and bust open all the parentheses and gather like terms. If you FOIL out y squared minus 1, you'll get, if you FOIL out y minus 1 squared, you'll get y squared minus 2y plus 1. And if you don't know where the minus 2y came from, and if you're wondering why is the 1 positive, I don't know what else to tell you besides stop distributing powers across minuses. Write that parentheses twice and FOIL it. You know who I'm talking to. If we distribute the -2, we get -2y plus 2. And when we combine like terms, we get x equals y squared minus 4y plus 3, which is the equation of a parabola. Granted, it's x is a function of y, not vice versa. That's why the parabola opens to the right instead of opening up or down. So that's one way to eliminate a parameter, is to solve for the parameter and then substitute into the other equation. Maybe clean it up a little bit like we did here. But this does justify that our parametric curve is indeed a parabola. There are other parametric equations where this is not the most efficient approach. As we run across them, I'll be sure to add them to our list of ways to eliminate a parameter.